to the Blemmings Labs room. It's my great pleasure to introduce the last session for the day, and that's Rafael Wysocki. Rafael is going to be speaking to us about the evolution of suspend-to-idle support in the Linux kernel. Rafael maintains the Linux kernel's power management infrastructure since 2009 and the core ACPI support code since 2012. He works at Intel in the System Software Engineering Division and focuses mainly on the mainline Linux kernel development. Rafael has been actively contributing to Linux since 2005, in particular to the kernel's Suspend Hibernate subsystem, power management in general, and hot plug infrastructure, ACPI and PCI support, and more. Before joining Intel in 2012, he worked at the Faculty of Physics at the University of Warsaw as a lecturer, sysadmin, and IT support specialist, and he ran a business of his own as a Linux and IT consultant. Rafael holds a PhD in physics from the University of Warsaw, Poland, and it's my great pleasure to welcome him to the stage. Please take it away, Rafael.
Thank you, Pia, for the introduction. Hello, everyone. Thanks. Welcome to my talk. Thanks for joining. Much appreciated. So I was going to introduce myself here, but since Pia did that, I can go straight to the material. So today I'm going to talk about Suspend-to-Idle, which is a variant of system suspend that allows the whole system to undergo a transition into a low power state. System-wide low power state, which is referred to as a sleep state. And in that state, the activity of the system is limited to basic maintenance. So this is the concept of a sleep state or of system sleep states is based on animal sleep, in which the body of the animal is not moving, like at least not very much. And what is the processes that are going in there are regarded as maintenance. So the same goes for a sleep state of a computer system. Also, the sleeping animals may be woken up from sleep by external events, and those events are that happen in the environment around the animal are referred to as wake-up events. And analogously, signals that cause the computer system in a sleep state to resume its normal operation are referred to as wake-up signals. Moreover, there are different kinds of sleep in animals, so they may be napping or they may be sleeping deeply, and so on. And also, analogously, computer systems may support multiple different sleep states, and the difference, one of the differences between them may be the time needed to resume the normal operation of the system after a wake-up signal or a wake-up event. Kind of for the completeness of terminology, the state of the system in which the normal activity happens is referred to as the working state. So you can imagine a state machine in which there is a working state and possibly multiple sleep states. And for each sleep state, there are two transitions from the working state to that sleep state, which is referred to as a suspend transition, and a transition from the sleep state to the working state, which is referred to as the resume transition. So the system starts in the working state, then after some time it may undergo a suspend transition to a sleep state, and then a wake-up event happens and the system undergoes a transition to the working state. And all of that is system-wide. So the suspend and resume transitions basically touch all of the devices in the system, or all of the hardware components in the system. So this is quite intrusive every time. So now because this is quite intrusive, the question is why bother? Why computer systems support something like sleep states. And obviously that's because there are use cases for it. And the use cases are canonical use cases for system sleep are the laptop in a base use case and the absent user use case. So in the laptop in a bag use case, the user closes the laptop lid, then puts the laptop in a bag, and it stays in a bag for some time, possibly a couple of days, even. And then the laptop is pulled out from the bag, and the lid is open, and the user expects the system to resume everything that it was doing before, right? So it should continue whatever it was doing before closing the lid. So obviously, in that case, it makes sense to, when a lid is closing, it makes sense to put the system into a sleep state, so as to save energy and also to prevent overheating. And the absent user use case is that basically a user goes away from the system or walks away from the system, leaves it alone, and the system is basically idle. And after some time, it may be put into a sleep state because it is not doing anything. So in order to save energy, it's better to put it to sleep. So these are the use cases. And now, because those use cases are there, the Linux and in particular the Linux kernel supports sleep states. And this slide illustrates the state machine that I was talking about and how it is, how it works in Linux at the high level. So the blue box at the top of the diagram is the working state. The gray boxes at the bottom are sleep states, and the transitions are represented as the workflow in the diagram. So the workflows, actually, the control flows. So the one on the left is referred to as platform-based suspend, which is the one that requires the platform firmware to be involved. And the one on the right-hand side is the Suspend-to-Idle, which is the really subject of my talk. And you can see that the difference between the two is that they're basically similar up to a point, and then the platform-based suspend transition needs to carry out some operations to prepare the system to for passing control over to the platform firmware at the last step. And one of those additional actions is to put all of the CPUs in the system except for one offline, which is quite intrusive and heavyweight operations. So this is the main difference between this and Suspend-to-Idle. And obviously also the platform firmware involvement is important. So the platform firmware takes over in the last step of system suspend in case of the platform-based suspend. Whereas in Suspend-to-Idle, the gray box, the sleep state, is managed by the Linux kernel and not by the platform firmware. The steps taken during the suspend transition are the notification, general notification that subsystems that are interested in receiving information about the upcoming system sleep transition are notified. Then user space is frozen, and some kernel threads are frozen as well, so they are prevented from running going forward. And then the devices are suspended in 4 phases. And the resume transition is the reverse of that. So devices are resumed again in 4 phases, and tasks are thawed, so they are allowed to run again. And notifications are sent to interested subsystems of the kernel that the transition was done. Yeah, and that part is similar, or actually analogous in both the suspend-to-idle and platform-based suspend cases. So the suspend-to-idle seems to be simpler, right? It doesn't involve the platform firmware, and it doesn't it doesn't require CPUs to be taken offline, right? So that seems to be simpler, but in fact it turns out that it is not so much, which I'm going to talk about later. And a control interface to trigger the suspend transition is based on SysFS. There are two files in SysFS for that. One of them is the state file, and the other is mem_sleep file. The state file is the actual interface to trigger a transition. Reading from it returns a list of strings, right? In the system from which this example comes from, there are three strings in this file. One is freeze, the other is mem, and the second is disk. So freeze it means suspend-to-idle. Freeze corresponds to suspend-to-idle. Mem represents whatever is selected by the mem_sleeps file, and disk is hibernation. So if you write freeze to syspower_state, for example, the system will go undergo a transition, suspend transition into the suspend-to-idle sleep state. Now the mem_sleep selects the sleep state which will be the target if mem is written to syspower_state. And again, reading from it returns a list of strings, and the current setting is shown in square brackets. So in this example, suspend-to-idle is the sleep state that will be entered when mem is written to syspower_state. And deep represents the platform-based suspend. So if you write deep to syspower mem_sleep, that it will become the sleep state associated with the mem string in syspower_state. In addition to that, there is an interface for controlling wake-up devices. Wake-up devices are devices that can wake up the system from sleep states and trigger the resume transition. For each of them, there is a wake-up file located in SysFS in the directory associated with a given device, and it can be written to with either enabled or disabled string. And enabled obviously means the device is allowed to generate wake-up signals resuming the system from sleep states. Disabled means that this is not allowed. And reading from this file returns the current setting. Right, so let's focus on suspend-to-idle going forward. And this slide summarizes the properties of it. So this is a system sleep state, right, in the first place. It's relatively lightweight, so it doesn't involve heavyweight operations like taking CPUs offline and invoking the platform firmware in the last step. It doesn't require the platform firmware to support it. It can use the support of platform firmware in order to improve the energy savings, but this is not required to support suspend-to-idle. Instead, it relies on CPU idle time management. So in order to support suspend-to-idle, the system must also support CPU idle time management, but that is the case in the majority of platforms where Linux can run. I'm actually not aware of any that don't support CPU idle time management, so that's vast majority. And Suspend-to-Idle also draws less power than any system state that can happen or any system configuration in the working state. All right, so these are the properties. And now I would like to talk about the history of it. So when it was introduced in the Linux kernel and how it's been changing over time, basically to explain how it works, but also this is an interesting story. So in my opinion, at least. So it all started in 2012, actually, when it was known that there would be systems, or at least PC systems like laptops and desktop systems, in which that CPU idle time management can go can get the system into a very low power state. So just through CPU idle time management. So on those systems, supporting platform-based suspend would not be necessary, or at least not very useful. And something would be used instead, right? Something had to be done instead. And the idea was, okay, so what if the CPUs are allowed to go into idle states when the devices have been suspended? So we ran the basic suspend code flow for platform-based suspend, but we stop when the devices have been suspended. In that case, in that situation, there shouldn't be much activity in the system. So hopefully, the CPUs will stay in idle states and until there is a wake-up event, and there will that will allow energy to be saved. Okay, so that was implemented in Linux 3.13 in 2014. And initial implementation was very simple, or I should say simplistic even, because the sleep state represented by the gray box under at the bottom of the slide, or the diagram, was implemented as a loop that was waiting for a variable called the wake up trigger, or actually it is not called the wake up trigger in the code, but this is what I'm calling it. This is a variable which initially is 0, and then it is changed to a non-zero value by one of the CPUs when it's woken up from the idle state in which it is staying. And then changing the value of that variable causes the loop to terminate and the resume transition to trigger. This is why I'm calling it a wake-up trigger. So the idea was that one of the CPUs would be woken up by an interrupt, and then it will set the wake-up trigger, and the system will resume. That's a good idea in principle, but there is a problem with how interrupts are handled in Linux during the system suspend and resume transitions. Because what happens is that after the three first phases of device suspend, or before the last phase of it, the interrupt handlers are prevented from running, and they are not allowed to run going forward until after the phase, the first phase of system resume. Actually, this is not entirely precise, because there are two levels of interrupt handlers in Linux. There are low-level handlers which handle interrupt controllers, and there are action handlers which are installed by device drivers, and they are responsible for handling individual devices. So the low-level handlers actually run all the time, but the action handlers are prevented from running after the third phase of device suspend. during the suspend transition. So now there's a problem because, you know, if the idea is to wake up the system from an interrupt handler, and interrupt handlers are prevented from running when the system is sleeping, then there is no way to wake it up, apparently. Well, it's not that bad because there are exceptions, and some interrupt action handlers actually for interrupt lines are allowed to run all the time. For example, timer interrupt handlers are allowed to run, to always run. But and those could be used to set the wake up trigger. So it was working, kind of working. But then in order for other devices to be able to wake up the system, their interrupt handlers would need to be modified to take this wake up case into account, and each of them would need to be changed, and that turned out to be impractical. So there was a wake up problem, and it was solved by handling this in the Irq subsystem. So the Irq subsystem was modified to mark all of the interrupt lines, or IRQs, that are configured for waking up the system with the enable underscore IRQ underscore wake call. The Irq subsystems marks them as wake up IRQs by setting a flag. The name of the flag is in the slide. And then when action handlers are prevented from running before the last phase of device suspend, another flag is set for all of the wake up IRQs. And that flag is checked by the Irq subsystem when an interrupt triggers. So even though action handlers cannot run, the Irq subsystem itself can check if the given interrupt is a wake-up interrupt, and if so, it will trigger the resume transition by setting the wake-up trigger. Otherwise, the system will stay in suspend. And the flow diagram at the bottom of the control flow at the bottom of the diagram represents the gray box that was shown in the previous slide. So the wake up problem was solved by modifying the Irq subsystem by to take care of handling wake up IRQs. This was implemented in Linux 3.19 in 2015, along with some other improvements which are not necessarily related to suspend-to-idle only. Were generic, like introducing the analyze suspend script for profiling system suspend and resume, which can help. It was renamed later, but could help to identify delays during those transitions, among other things. There was another feature called Direct Complete, which allowed devices that were suspended in the working state to stay in suspend over the both suspend and resume transitions and in the sleep state. Also, Suspend-to-Idle was starting to use the deepest idle state in the ACPI idle time management, and all of the device suspend and resume phases were made asynchronous, so the callbacks are called in parallel with each other, generally speaking. Okay, so it improved quite a bit, and it triggered some more people to poke at it, and another problem was reported as a result of that. And as that was related to timers, and specifically to kernel timers that were periodic. So a periodic timer is a timer whose timer function reschedules itself, right? So it runs and schedules the same timer again after a specific time, and then as a result, the timer triggers periodically over time, and that is not desirable when the system is sleeping, right? When the system is in a sleep state and we have a periodic timer, then such a timer will disturb the CPUs, right? Because at least one of them will have to wake up every time the timer triggers and handle the timer, and then go back to idle, to an idle state. And so the aperiodic timer that is triggering while in a sleep state can reduce or can cause the power drawn in the sleep state to grow, right? So when the timer, such a timer is present, the system draws more power than it could otherwise. And if the period of the timer is small or relatively small, this is not a problem. But if the timer, the period of the timer is short, then this really prevents much energy from being saved. So the whole transition to a sleep state is basically pointless from that perspective, and something had to be done to deal with that. And the solution was quite straightforward, but also not very easy to implement. So the idea was to suspend the whole timekeeping of the kernel when the last CPU goes to an during the while in the sleep state, right? So obviously we want all of the CPUs to go into idle states at the same time. And when the last of them goes to an idle state, it will suspend the timekeeping, which prevents timers from triggering at all. This solution was suggested by Thomas Gleixner, and it was implemented in Linux 4.4 in 2016. Also, in Linux 4.4, wakeup IRQ framework was added to handle systems in which there are interrupt lines dedicated for system wakeup. There are systems like that where there's some interrupt lines are just for this purpose, and so the framework was added to the kernel to deal with this case. Okay, so far so good, but there was another problem which was related to the control interface I was talking about, and that's why I was spending so much time on it. So the problem was that at that time the only way to trigger a transition to suspend to idle was to write freeze to syspower state, to the state file, and the problem was that actually none of the desktop environments available at that time was recognizing the freeze string, and none of them was using it. So if users wanted to use suspend to idle, that they had to do that manually, and it was kind of feeling like driving a historic car, in which you have to do everything manually, including opening the engine compartment when you want to cool it down sometimes, right? So this is like not a very good experience from the user's perspective. So that's why the control interface was changed to the one that is present today, and with the mem_sleep file to control what the mem string means. All right, so this the interface was changed in Linux 4.10 and in 2017, and that was done along with adding device link support to the kernel. And device links are a feature allowing the non-hierarchical dependencies between devices to be represented in the kernel. and that is important for the device suspend and resume ordering. So at this point, everybody was happy, like from everybody, all the system suspend developments were happy with this, and we thought that this is how it should look like, and now we can go and fix drivers to work correctly with system suspend and resume instead of hacking on the core. But what happened that it was not exactly the case, and it's kind of similar to what happens to a teenager who goes to a college or a university, depending on the country, and I think that they are smart and grown up enough to take care of themselves, and it's maybe even the case, but there are challenges that needs to be faced, right? There are challenges that happen, and a young person can have to deal with them, or has to, sorry. So that happens to the suspend-to-idle development as well, and the challenge happened. And the challenge was that somebody in industry thought that it would be a good idea to use the same interrupt line for signaling wake up and non-wake up events. And specifically, that also happened when the system was in suspend-to-idle. And the hierarchy line in question was the ACPI SCI interrupt. The SCI stands for System Control Interrupt. So that was related to the embedded controller. So the SCI is a multiplex interrupt which handles or which is used to signal multiple different types of events, and for example, device wake up events are signaled through the SCI, or PCI PME, which also are the type of wake up events, power management events on the PCI bus. But also the SCI is used to signal events from the embedded controller, such as battery monitoring events or thermal events, and they are not wake-up events, generally speaking. The embedded controller is a microcontroller which runs its own program, and it controls some internal platform activities like thermal monitoring, battery monitoring, and so on. So what happened was that the power button, which previously was just a single just binary button, like it could be pressed or not, started to be used as a button, as a button array with multiple states, right? So it can be pressed, released, pressed and held, and so on. And that there are several states of a power button that was recognized. And somebody had an idea that, well, that could be done by the embedded controller. Okay, because the embedded controller is running anyway, so why cannot be used to handle the power button events and signal them to the operating system through the ACPI SCI? Well, that's all fine, except when the system is in a sleep state, like suspend-to-idle, because the power button events are wake-up events, like other events signaled through the SCI, but also the embedded controller signals other types of events like battery and thermal. And before adding the power button support to the embedded controller, it was possible to actually disable the embedded controller signal line before putting the system into sleep. But now this cannot be done, and in which case, obviously, the non-wake-up events will be filtered out. But now it cannot be done because of the power button thing, right? So in fact, we need to deal with a interrupt line which can be used both to signal wake-up events and to signal something that is not a wake-up event and should be ignored while sleeping. So there was an attempt to handle it or to implement a handling of it in Linux 4.15 in 2018. And the idea was that when the interrupts were, or the interrupt handlers were allowed to run again after the first phase of system resume, there would be a check if this really is a wake up, a resume transition, or the system should go back to sleep. And if it should go back to sleep, then the last phase of system suspend was retriggered, and the system was going back to the sleep state represented by the gray button at the bottom of the diagram. But unfortunately, that didn't work really, because it confused device drivers. Because it turns out that some device drivers has split suspend and resume, such that it happens in two phases, for example. And running just one phase without the other may be confusing to the driver and so on. So this was not working as expected, and this idea was finally abandoned. And what was done instead is shown in this diagram. The part on the left-hand side is old, is what was there already. This is the timekeeping suspend, right? Timekeeping handling. Because of the interrupt problem, and the green part on the right-hand side is the new one, and that implements the handling of, or the handling of SCI. So when there is a wake-up interrupt, which is recognized by the Irq Subsystem, the code flow checks if this is an ACPI SCI. If it isn't, the system can resume, right? If it is an SCI, it needs to be checked if that is an EC event. If that is an EC event, then the wake up is canceled by incrementing the wake up trigger, and also clearing the setting the armed flag for the SCI again. And EC events are processed, and if any of them means a wake up event, the system will resume. Otherwise, it will go back to sleep, which means that the CPUs will become idle. They will go into idle states, and the last one will suspend the timekeeping and so on, right? So now the logic to handle this is implemented in the or as part of the gray box at the bottom of the diagram, and that gray box represents the entire code flow that I was showing in the previous slide. So this is what happens today, which is as of the end of 2020. So the sleep state, which is represented by the gray box, is actually quite a complicated workflow, which may involve things like running, processing the EC events, which involves invoking the ACPI bytecode interpreter, for example. So this may be a complicated workflow. But that's how it goes, right? Because it has to be like that. All right, and now if you think about, if you look at the history that I told you, then this is this illustrates how the virtuous cycle of kernel development works. So basically, there is a generic idea or basic idea which all of that is based on. And what happens, the code is implemented to implement this idea. The code is written. Then people start using it. Then problems happen and they are reported. Tools are developed in order to diagnose those problems. and developers get more understanding and better understanding of the problems that happen, and code is improved, right? And this happens for multiple times. And if you look at the evolution of Suspend-to-Idle support, it actually really this cycle actually went for a few, or has gone for a few times in there. There were a few iterations of the cycle involved, right, in this development. So this illustrates very well how the kernel is developed, how its development works. All right, and with that, we can look kind of optimistically into the future. Hopefully, there will be no challenges against Suspend-to-Idle, like the last one I was talking about, or if they are, then we can deal with them. And now we can go and look into individual drivers instead of hacking on the core, right? So if you have any questions or comments or concerns, or you have ideas about how to improve it, please let me know. And thank you for your attention.
Wonderful. Thank you so much. There was a lot in that. I actually had a few people say they kept thinking of questions, but then you kept answering the questions as we were going. So that's a pretty good start. So we do have one question from Jeremy Kerr. Did the timekeeping suspend change suppress legitimate wake-up events? Were there drivers that check for wake-up events as part of a timer callback?
No, so the wake-up events, so timers as the, okay, I need to go back to this. So what I was talking about were timers that are using the software timers. Okay, so software timers that are using the same timer interrupt, all of them, and the timer interrupts is like a local API timer interrupt or similar. So this cannot be a wake up interrupt.
Okay.
So the answer is, so this cannot be a wake up interrupt. So the answer is no. The timekeeping suspend doesn't prevent legitimate wake up events from happening.
Okay, wonderful. If anyone has any questions, please post them in. I'm going to ask you a slightly different question. You've obviously been in this space and thinking about this for a long time. I guess the question I have for you is, where do you see suspend going? Some systems are clearly, as we move forward, never going to suspend. Does moving to solid state, do you think, make it less relevant for some devices moving forward? Like, where do you see this going in 5 or 10 or 15 years?
So one of the obvious things or obvious improvements is if persistent memory is used in systems, right? Because it doesn't change the flow a bit that much, but so today obviously in order to preserve the contents of memory, it has to be in a self-refresh mode, which draws power. If we have persistent memory, then it will just be able to turn power off, basically, when almost, because we still need to wake up devices still need to be on in order for us to be able to wake up the system, but the memory could be turned off, and that could be quite a bit of energy saving. So this is promising, but where this is, it is really hard to say. So I'm really seeing the direction in which the people will want to turn more and more devices off while sleeping, right? So this is like more things off, so as to reduce the power drawn. But the flow, I'm not sure if it will change that much.
Okay. So I have another question from you, Gyuda. Apologies if I pronounced that incorrectly. But that's the question. If I run a distro kernel, like say 5.4 for Ubuntu LTS, does that mean suspend-to-idle cannot possibly work?
No, so it can work. In some cases, it will be used by default even, which you may notice if you poke at the interface that I was talking about. You need to check what is the default option in the mem_sleep file. If that's s2idle, then the suspend-to-idle is going to be used by default. But you can switch it. The SSFS interface can be used to set the default suspend action for the distribution. So that should not be a problem, really.
Wonderful. Well, we're at time. Thank you so much for the presentation.
Thank you.
Just for everyone else, there is the Lemmings Labs post-talk Q&A channel on Venulus. If you want to have a discussion, follow up with any of the speakers actually from the day, from today's sessions, then please do join that channel so that you can follow up in the conversation. And if you wouldn't mind joining in that conversation, that would be really great. And that's the end of today. That's the last session for today. So we will see you all tomorrow after the keynote, and hopefully you'll be joining us for some of the Lemmings Labs room talks tomorrow. So we'll see you all tomorrow. Thank you so much. And thank you again, Rafael. Really appreciate the presentation today.
Thank you. Thank you.